Hi, my name is Alceste Scalas.
And my name is Ivan Prokić.
And we now present our paper Precise Subtyping for Asynchronous Multiparty Sessions. This is joint work with Silvia Ghilezan, Jovanka Pantović and Nobuko Yoshida. The title of our paper summarizes our main contribution. We present the first formalization of the precise subtyping relation for asynchronous multiparty sessions. Precise means that our subtyping is both sound, so it respects the Liskov substitution principle, and it is also complete. It cannot be extended, because any larger subtyping is unsound. And in this talk, we will explain how we achieve these results and also how asynchrony brings several challenges that we overcome by introducing a novel session decomposition technique. Let's begin with a simple motivating example. Let's say that we are developing a distributed computing system where there are several participants, P, Q, and R, and each participant is running its own process, and the process P is written like this. So the process is first waiting a message from participant Q. The message can be either done or fail, and then if the message is done, then the process sends either continue or stop to participant R. Otherwise, if the message from Q is fail, the process checks whether the failure is fatal and then sends continue or stop to participant R. Observe that in this example, the process is first receiving from Q and then sending to R. This means that participant R needs to wait for participant P, who in turn is waiting for participant Q. So we may want to optimize this system and let participant R run immediately. And to do that, we may want to replace the process P above with this variant, where essentially the process immediately sends continue or stop to participant R and then receives the message done or fail from Q. So there is now a reordering of the send and receive operations because now P first sends to R and then receives from Q. And now we may wonder, is this process replacement correct? Can this cause any error? Let's find out using session subtyping.
Now, let us step back for a moment to say, what does the notion of subtyping mean in programming languages theory? Well, the subtyping can be explained in simple terms of Liskov substitution principle, saying that any object of subtype can be safely used in any context where an object of supertype is expected. And the same principle applies when it comes to message passing programs, where now any process of subtype can be safely used whenever a process of supertype is expected. So the subtyping establishes a principle for safe process replacements, and that is exactly what we need. Now, we want to characterize safe replacements of processes that are involved in communication protocols. And this is why we are talking about session types, since session types are type formalism used to model structured communication. For instance, to the process P from our opening example, we can assign a session type T that models the behavior of the process. So the type T, same as the process P, first specifies receiving from participant Q either message done, but now payload is typed as integer, or message fail with the payload typed as boolean. And in both cases, it continues by sending to participant R either message cont with the payload typed as integer, or message stop with the payload typed as unit. Now, we can use the existing subtyping for multi-party session types for the synchronous case to optimize type T through the subtyping, but that actually allows us only to offer for a subtype to offer more branches in inputs, like in the type that we have on the left hand side, that is a subtype of type T, and the subtype can also be optimized type T through offering less possibilities in the output places, like the type that we have on the right hand side. But these optimizations are not the ones that we want, since we want to capture input-output reorderings. What ideally we would want to is to have a subtype of type T that first specifies sending to participant R and then receiving from participant Q.
Intuitively, some reorderings of inputs and outputs should be allowed because we are considering asynchronous sessions. So send operations are non-blocking and the message delivery occurs through first-in, first-out buffers. For example, consider our opening scenario, where process P is waiting for a message from Q, so when Q sends it, the message is buffered, and then P receives it, and then P can send a message to R, who receives it later. Now, in this asynchronous setting, our optimization, where P sends to R and then receives from Q, would work like this. P sends a message immediately, and then maybe in the meanwhile Q may send a message to P, and then R can receive the message, and P can receive its message as well. So it looks like that asynchrony allows this optimization. This should be correct. It should be possible to replace a process that first receives and then sends with a process that first sends and then receives. So how can we define a subtyping to allow for it? And is there any other reordering we should allow to? So our goal is to find the best subtyping for asynchronous multiparty sessions. And here is what we mean by best. In programming languages, subtypings must be sound. So if T' is subtype of T, then it must be the case that any object of type T' can be used in any context expecting an object of type T. Now let's consider the reverse implication. If it is always safe to use an object of type T' instead of an object of type T, then T' is subtype of T. A subtyping that has this property is called complete. And if a subtyping is both sound and complete, then it is precise. This topic has been studied by Dezzani, Blackburn, Di Gatti, and Ghilezan in the context of the lambda calculus. Now what we want to do is apply the same framework but in the context of multiparty session types. So we are looking for the sound and complete session subtyping relation between multiparty session types, a relation that allows to safely replace processes instead of objects and that covers exactly all the safe reorderings of send and receive operations, for instance the one in our opening example. There is some previous work on the topic, but it only covers binary sessions, so with two participants, or multiparty synchronous sessions, where input and output reorderings are not allowed.
Our formalism is a standard single session calculus with types. A session is parallel composition of processes assigned to participants with the corresponding queues. We have seen already much of the syntax of processes and types through our examples. I just want to point out that the syntaxes also include recursive processes and recursive session types. Our type judgment states that all participants in the session behave as prescribed with the type context gamma, and gamma is a collection of type assumptions where to each participant in the session we assign a type of its queue and a type of its process, the session type. Our type system checks if session respects the type assumptions, and it uses a relatively novel approach developed by Scalas and Yoshida that do not use global session types as in many other works on multiparty session types, but instead uses behavioral properties of type context. And specifically in our work we consider live typing context having no type level errors, and by errors we consider deadlocks, communication mismatches, orphan messages, and starvation.
Before proceeding, let's have a look at what kind of errors we want to avoid. A deadlock happens when all processes in a system get stuck, waiting for a message from another. A communication mismatch happens when a process sends a message that the recipient does not support. An orphan message happens when a process sends a message but the intended recipient never reads it. Finally, a starvation error happens when a process like R is expecting a message from P, but P is busy interacting with another process and never sends that message.
Before showing our key insight, let us first see what are the challenges for defining the precise subtyping for asynchronous multi-party session types. Well, for starters, we have that our subtyping has to subsume the synchronous one, and as we already discussed in one of the previous slides, this means that subtype can be used to optimize type through offering more choices in inputs and less choices in outputs. But since we are dealing with the asynchronous subtyping, it also has to capture all safe send receive reorderings. And this can be first, the subtyping can be used to first anticipate outputs before inputs, like in this first example here where we have that type specifies first input from Q and then output to R, and the subtype anticipates the output to R and only then performs the input to Q. Then the subtyping can also be used to anticipate inputs over inputs if we have different participants in both inputs. Like in this example, we have that type specifies first input from Q and then input from R, and the subtype anticipates the input to R and only then perform input to Q. And the same principle applies for anticipating outputs over outputs if the outputs are from different participants, like in this example here where we have the type specifies first output to R and then first output to Q and then output to R, while the subtype anticipates the output to R and only then performs output to Q. So, and these message reorderings are the ones that are hard to formalize for all possible session types. And our approach here is, and our idea here is to use session decomposition. So what is the session decomposition? First, we consider, we use standard tree representation of session types, but instead of characterizing input-output reorderings directly for all session trees, we first decompose trees into three forms. First is single input, then we have single output, and finally single input, single output trees. And then we formalize message reorderings only for single input, single output trees. So we define a refinement relation for SISO trees, and only at this level we deal with these message reorderings that are safe. So these SISO trees are only sequences of input and output actions. So before showing the refinement relation for single input, single output trees, let us first explain what is this session decomposition. So we define two functions, one taking indexed with SI, taking as an argument session tree, and producing a set of all single input trees by pruning the tree in all branches in the inputs. So for instance, if we take this type T and apply SI function, it will produce a set of two single input types trees, that one following the message done in this input and the second following message fail. Similarly, we have the function SO, single output, that takes as an argument a tree and produces a set of single output trees. So for instance, if we take this type, the above type T prime, and apply function SO, we will obtain a set of two single output trees, one following message cont in this output and the second following message stop. Now we can see how we define the SISO refinement. So again, SISO trees are just paths. These are only sequences of inputs and outputs. And we define SISO refinement by these 5 coinductive rules, and only these 2 rules are actually defining what are the safe reorderings for SISO trees. So this first rule on the right hand side says that an input from P can be anticipated over a finite sequence. So this AP stands for a finite sequence of inputs, where none of these inputs is from the same participant P. So we can swap inputs if the inputs are not directed to the same participant. And similarly, the second rule on the right hand side says that we can anticipate output to P over finite number of both inputs and outputs, as long as none of these outputs is directed to the same participant P. This is defined by this PB sequence here. So it can be both inputs, it can be outputs, as long as the outputs are not directed to the same participant P. And that's it. These two simple rules define all safe reorderings for SISO trees.
We now have all the ingredients to define our asynchronous multi-party session subtyping relation. And it looks like this. It says that T prime is subtype of T if, when we take all the single output trees of T prime and all the single input trees of T, then we can find matching pairs of single input and single output trees that are in the relation, in the refinement of the previous slide. I will illustrate this with an example. Let's take the types of our opening example, where we have T, which is the type that first receives from Q and then sends to R, and T prime is the type that first sends to R and then receives from Q. We want to show that T prime is a subtype of T. To do that, according to the definition, we need to take first the single output subtrees of T prime, the subtype. And this is the result. This is a set with two types. Each one has outputs with single choices, continue or stop. We also take the single input decomposition of the type on the right, of the supertype. And this gives this set where we have two types. One has the single input done and the other has the single input fail. Now, to show that the relation holds, we need to find pairs of single input, single output trees inside these sets that are related by the refinement in the previous slide. And these related pairs are highlighted here. You can observe, for instance, that in this pair, we have on the right, we have an input followed by an output, while on the left, we have an output followed by an input. And the other cases are similar. So by finding these matching pairs, we satisfy all the quantifications in the definition, and therefore we prove that T prime is a subtype of T.
Now let us see what are the results we have for our subtyping relation. First, our subtyping relation is a preorder. And then to show that our subtyping is sound, we first show the subject reduction statement, and that is that if a session is typed with the live typing environment and it reduces to some M prime session, then M prime is also typed with some live typing environment. And directly from the subject reduction, we obtain type safety, saying that if a session is typed with live typing environment, then it will never incur in an error. And by errors, as we said, we consider deadlocks, communication mismatches, orphan messages, and starvation. And as a direct consequence of type safety, we obtain that our asynchronous session subtyping is sound, meaning that any process of subtype can be safely used in any session expecting a process of supertype. So, in order to show that our relation is precise, we also need to show the completeness result. And the completeness means that if any process of type T prime can be safely used in any session expecting a process of type T, then it must hold that T prime is subtype of T. And our approach in showing this is actually to prove the contrapositive of the completeness statement, and that is, if T prime is not subtype of T, then we can find a session that is safe when composed with any process of type T, but causes an error when composed with some process of type T prime. And how we show this? Well, in first step, we get a precise description of T prime and T, for which it holds that T prime is not subtype of T. Then, given type T, we define a characteristic process that is typable with T. Then, given type T, we also define a characteristic session that is typable when composed with any process of type T. And finally, we show that given that T prime is not subtype of T, we show that composing characteristic process of T prime with characteristic session of T results in an error. But this proof actually is quite complicated for multiparty asynchronous session types, and this is another place where decomposition technique actually helps. We actually did not have to concentrate on all possible session types for which this negative subtyping holds, but we actually could concentrate ourselves only on single input, single output types. And for details, you can please check the paper.
So we have proven our main result. Our asynchronous multiparty session subtyping is sound and complete and therefore precise. In the paper, there are more preciseness results. In particular, if we interpret types as sets of typed processes, we can prove that our subtyping is denotationally precise. Also, if we interpret session types as communicating automata, then we can prove that our subtyping is precise with respect to liveness for the replacement of automata. I will not go into details. You can find these results in section 7 of the paper, and they all descend from our main result.
Okay, let's now recap. We have presented the first formalization of the precise subtyping for asynchronous multiparty sessions. Up to now, the preciseness of the subtyping were proved for binary sessions both in synchronous and asynchronous case by Chen and others in the paper published in 2017, where binary actually means that these sessions are modeling only communications between two participants. For multi-party sessions, for the synchronous case, Ghilezan and others in the paper published in 2019 showed the preciseness of the subtyping relation, and as we said, this is the first work that presents the precise subtyping for asynchronous multiparty sessions. So let's repeat again what precise stands for. It stands for that our subtyping is sound, and that is that it guarantees safe process replacements, and also complete, that any larger subtyping gets unsound. Okay, then we have presented what were the obstacles in defining the precise subtyping and proving that is precise for asynchronous multiparty sessions, and we showed how our novel session decomposition technique helps to tame the complexity of formalization and proofs. Okay, that would be all from me. Thank you for listening, and we are looking forward to hear your questions and comments in the Q&A session.